Let's have a little fun with some polar numbers. In particular here, we're going to take a square root of a polar number. So I just want to show graphically what's going on. So here I have the complex plane where the real axis is the x-axis and the imaginary axis is the y-axis. And so the complex number -2 plus 4i looks a lot like the point -2, 4 here. So that's my point -2, 4i there. And I've also graphed it in polar form where I'm showing the radius of this thing here and I have its angle there. So we'll calculate that angle and its length in a minute in polar form. Now the square root of this number, if you think about Euler's formula, so Euler's formula tells us that a complex number can be written in the form r times e to the I theta, where r is the distance to the pole and theta is the angle from the positive real axis here. And that also can be expressed as r times parentheses cosine of theta plus I sine of theta. And so this takes us in between. This polar form can be evaluated to give us the component form of this complex number, or we can write it in the Euler's version of the polar form, which is kind of neat. Nice thing about that is if you're taking a square root of a number, for example, I want to take the square root of -2 plus 4i, then if I know its radius, its distance to the pole, and the angle it makes with the positive real axis there, then that's just a matter of taking my r times e to the I theta, and a square root is the power 1/2, and then I just have a power to a power. So then I'm going to have the square root of that radius. And power to a power here, we multiply, so that gives me e to the I times theta times 1/2, which is I'm just going to write as theta over 2, which means I just need half of this angle. And you can see this point B I plotted here is it bisects this angle alpha here. Now, it turns out numbers have 2 square roots. And so there is another version of this square root polar complex number here over here, point C. And imagine its angle, which would be this angle right there. And if this number here is the square root, if I square this number here, I will get my original number back. And if I square a complex number, that doubles the angle. So imagine doubling this right angle, what'll happen is I'll get right back to my original point there. So there are 2 points in the complex plane here whose square is the point -2 plus 4i. So now we need to find those 2 points. And Euler's formula is going to help us do that. To use Euler's formula, I need to know what r is over here. And that's just the Pythagorean theorem. So r is going to be equal to the square root of -2 squared plus 4 squared. So that's 4 plus 16 on a good day is 20. So r is the square root of 20. And I'm going to have to take the square root of that in a moment to get the square root of the complex number here. So that's the r I want right there. And the angle we can find by using the arctangent. So if I take the arctangent of the y value, which is the 4 with the I, over the x value, -2. Now, slight problem with this to get theta is the arctangent only knows about angles from 180 down to -180 or vice versa here. It only knows angles in these 2 quadrants. So what the arctangent is going to return to me, it's going to return to me this angle over here. So it's going to give me that negative angle. And I want to just translate that up over to that angle here. So I'm just going to add 180 to get that. So I'm going to have to take whatever the arctangent tells me and add 180 degrees to that. And my claim is that's about 116. So I'm just going to double check that on a calculator. So here I have my Desmos calculator, which I did 2 things. I put it in polar mode so I can kind of see angles there with degrees. And then I put it in degree mode instead of radian mode. So I would have to be conscious of our angle. And then I want the arctan inverse tangent of 4 over -2, which is just -2. And then I want to add 180 to that. And there's that 116 that I had in my image. Okay. So I found my theta and I found my r. So now to find the square root of this number here, I just put that together. So let's write that down here. So this number here is approximately, let's call it 116.565. And make sure we label that as degrees so we don't confuse it with radians. And then square root of 20, I'm just going to leave that as the square root of 20. Let's see, I could use 1 decimal place nearest degree. It says should also work there. So let's see, so what would that be? 116.6 degrees. And then for the square root of 20, so we can do the exact answer exactly or approximately here. Square root of 20 is about 4.5-ish. And then I need the square root of that for this. So again, this says that the square root of -2 plus 4i, at least one of those square roots, is going to be equal to the square root of whatever I found for r. So I'm going to write a wavy equals because I've rounded there. So that would be the square root of about 4.5. I'm kind of making a problem for myself here because this is I've approximated the square root and I'm about to approximate it again. So that's a little sketchy. We'll fix that in a moment. Times e to the power I, and then theta over 2. So 116.6 over 2. So what's that going to give me? 58.3, about 58.3 degrees. And if I look at my picture, would you buy to get to that green point there? That's about 58.3 degrees. Yeah, that's pretty close to 60, which is this line right here, just a hair under it there. So that's approximately one of these complex points. And then I can use the r cosine theta I sine theta to then convert it to standard form of a complex number. Now, what about this other one here? Well, the bottom line is to find the other one, I could just think of this original angle alpha here as alpha plus 360 and then cut it in half, and that'll give me that one right there. So for the other one, let's do that one in red. So the other root just simply comes from taking my alpha here, adding 360 to it. And so this essentially right here is my alpha plus 360 and then divide by 2. So I guess I should have labeled that alpha. On my picture, it's alpha. And that right there is my other angle, and I just swap that in there and I have my other point there. So let's go to a calculator and find each of those. And we'll use the features of the calculator so we don't have to worry about rounding. Like the calculator saved that number for me. So I'm going to call that number right there R. Oh, it doesn't like R. Let's call it something else. How about we call it, what are we going to call that? Elemental P, Q, R, S. I'm just going to call it, I don't like that it's graphing that circle. Maybe if I call it capital R, there we go. Okay, so that's the radius of the original point here. And then we need its square root for our imaginary number. And then let's calculate our angle. I'm going to call that one A. And A we found by, ooh, I already have it up here. I'm just going to call that sucker A right there. So that's my original angle, that 116. Oops, and I just need to cut that in half. Okay, so this is the angle for that point. This is the radius for that point. So the new polar point then, I'm going to put it in point form, is going to be the square root of R times the cosine of this angle over 2. So square root of this number here, so the square root of the square root of 20, which I can just do square root of R to get that. It's about 2.1. And then we want to multiply that by the cosine of our alpha over 2, which I'm calling a here, so just a over 2, comma, or we would write plus I on paper. We'll do that in a moment. Again, that's square root of r times the sine of that angle alpha over 2, which I'm calling a over 2 here. And here you can see that point right there is just below that 60-degree line there. And this radius up here, square root of 20, is a little over 4, between 4 and 5. So the square root of that length should be a little over 2, right? So that looks good. And if I want those values there, let's see, is there a way to get, yeah, if I just click on the point, then Desmos will show me approximations of those values. So this is kind of the exact form right there with those numbers. The other point, we'd have to take alpha plus 360 and then cut it in half. And again, we could clean all that up with a little arithmetic, but I don't think there's really a big need for that. So the other point is going to have the same radius, which is that square root of r, but the angle is going to be a little bit different. So the cosine here is going to get a fraction with my a for alpha plus 360, and then divide by 2. And then we do similarly for the imaginary part. It's going to be, again, that square root of r times the sine of the fraction a plus 360 over 2. Oops, 2. Close the sign, close the point, and here I can see that other one, and those two connect each other, really. They're 180 degrees apart, those 2 points, and they have the same radius. And if I take the angle formed by that black line and the pole here, the black point and the pole to the x-axis, if I double that angle, I should get the angle of my original point back. And similarly, if I think about the angle for this point down here, if I double that angle, that'll take me over here. So if I click on that, it will show me the exact value of that point right there. And so we get some reflective symmetry going on, the negative 1.12, negative 1.799, positive 1.12, positive 1.799. And so in complex form, if I use just one decimal place each, we get 1.1 and 1.8-ish, approximately. So this one here would be about 1.1 plus I times 1.8 or 1.8I, either way is fine. And this one would be negative 1.1 plus, minus I times 1.8 or 1.8I to one decimal place. And if we wanted them exactly, well, we can do that exactly too. The exact version of the angle is kind of complicated, right? The first angle is the arctan of negative 2 plus 180. So if you really, really, really wanted an exact answer, W1, let's do that in green, omega 1 would be the square root of 20 times the cosine, and then the angle would be the arctan of negative 2 plus 180, parentheses there, divided by 2 plus I times the sine of, and our angle again for the original one was arctan of negative 2 plus 180, and that fraction is over 2. And so again, it's plus I, right? So that's the complex form of that right there. So that'd be omega 1, and then omega 2. The other point, if you wanted the exact value, you would have to add a 360 in addition to the 180 up there to get the other one. The important thing I wanted to show you here, again, 2 things. One, complex points can be represented in polar form. That polar form has a radius and an angle. And if I take a power of a complex number, that means take the power of the radius and then multiply that power by the angle, and that gives you the power of the complex number. So this Euler's formula really makes powers, and a root is a power, much, much easier to deal with. Thank you. Have fun. Do good math.